Humans process reality by synthesizing simultaneous data streams. When listening to someone speak, your brain isn't just processing sound waves. It actively cross-references that audio with the visual shape of the speaker's mouth. This dependence is most apparent in the McGurk effect. If you watch a video of a person mouthing gaga while the audio track plays baba, your brain resolves the conflict by making you hear a third, completely distinct sound, dada. Visual information can entirely override conflicting audio data. For decades, artificial intelligence lacked this synthetic capability. Engineers were forced to build highly rigid, specialized processing pipelines for every individual sense. To transcribe audio, you historically built a sequence of hidden Markov models to calculate the precise probability of specific sounds. To recognize objects, you relied on support vector machines. Vision models and text models existed in entirely separate mathematical universes. This architectural flowchart represents the destination of modern AI, the Unified Foundation model. Instead of isolating data streams, a natively multimodal system routes vision, audio, and text into a single massive neural network. The transition to modern AI was defined by the total collapse of handcrafted feature extraction in favor of continuous vector spaces. To build a system capable of understanding context like a human, the industry abandoned writing hard-coded rules and began teaching machines a shared mathematical language. The raw data problem of computer vision is rooted in the birth of early digital photography. When Steven Sasson invented this device at Kodak in 1975, he captured the physical world in a format a machine could finally read. This grid is exactly what an image is to a machine, an array where each number represents a pixel's brightness intensity from 0 to 255. In the classic 2000s architecture, human experts had to bridge the gap between these raw pixels and the final classification. This required manual feature extraction. Engineers wrote mathematical formulas to instruct the computer to look for distinct clues, like sharp changes in brightness to identify an edge, or the specific intensity of a color channel. The Viola-Jones face detector of 2004 was the peak of this era. It relied on carefully designed HAR-like features to measure brightness differences, calculating that the bridge of a nose is usually brighter than the eye sockets. However, the classic pipeline hit a ceiling. Human engineers cannot mathematically describe every feature of a complex, chaotic reality. The high engineering effort required for these handcrafted features resulted in brittle systems that failed to generalize beyond very narrow, controlled tasks. The paradigm shift came with end-to-end learning, where artificial neural networks replaced the manual pipeline. While a single mathematical neuron is effective at basic logic, it possesses a fundamental limitation when faced with nonlinear problems. This XOR logic gate graph shows how no single straight line can separate positive results from negative ones. A single-layer model fails here. The solution is the multi-layer perceptron. Inserting a hidden neuron layer gives the network the capacity to map complex, nonlinear relationships. These hidden layers allow the network to discover and combine nonlinear patterns on its own, solving the logic problems that a single neuron would miss. Stacking these hidden layers gave the architecture the mathematical capacity to learn its own feature representations directly from raw data, making human engineering obsolete. If humans aren't writing the mathematical rules for feature extraction, how does the network discover them?
This topographical map shows the network's starting condition. Initialized with random weights, it makes a blind prediction. The resulting error places it on the outer ring of the loss landscape. To reduce this, the system employs stochastic gradient descent. The network calculates the gradient, the steepest downward slope from its current position, and updates its parameters to take a step in that direction. The learning rate determines exactly how large that step toward the center valley will be. In this computational graph, backpropagation enables updates. It begins with a forward pass, flowing data through layers to calculate final loss. Then the backward pass uses the chain rule to move in reverse, distributing exact mathematical blame to every weight and bias. This constant loop of forward predictions and backward updates forces the network to continuously refine its internal features. This specific mathematical optimization engine is what allowed machines to write their own optimal rules directly from the raw data they process.
The practical impact of this math was proven in 2012, when a deep learning model triggered a massive drop in the classification error rate at the ImageNet visual recognition competition. That model, AlexNet, demonstrated that convolutional neural networks build a rigid feature hierarchy. The early layers identify basic edges and textures, while deeper layers combine those patterns to recognize complex objects like wheels or faces. This same shift occurred in natural language processing. Engineers moved past traditional methods of counting word frequencies and applied the neural approach to text. This 3D graph visualizes word embeddings, translating vocabulary into a continuous vector space. Words appearing in similar contexts, like Sunday and Monday, occupy the same region. Linguistic meaning becomes measurable geography, where distance reflects actual semantic relationships. You can see this through vector arithmetic. If you take the mathematical vector for king, subtract man, and add woman, the resulting coordinates align almost perfectly with the vector for queen. This is the critical synthesis. Whether a network is processing the pixels of an image or the semantics of a royal title, deep learning maps all variations of reality into shared, differentiable vector spaces. Returning to the Qwen-3 Omni diagram, we can see the practical application of these vector spaces in modern foundation models. The unified input phase ensures that incoming audio waves, image pixels, and text characters are all immediately converted into identical mathematical tokens. Because the format is identical, all of these tokens can feed directly into a single massive neural network, typically a transformer or a mixture of experts, which acts as the central thinker. Because all data lives within a shared architecture, the model can engage in transfer learning. The internal logic and grammar learned from processing text can directly aid the model in identifying structures in audio or visual patterns. Maintaining these unified systems requires a significant investment in hardware and the vast volume of training data needed to refine the network. It also forces a transparency trade-off. We have moved from interpretable, hand-engineered pipelines to generalized black box models where millions of internal connections determine the output. This trade-off was necessary. By surrendering our manual rules to the process of mathematical mapping, we have finally built artificial intelligence systems that are able to perceive the unified, multimodal reality of the human experience.